First of all, I really, thank you for your kind invitation. I'm very much honored to give my talk to all of you. Actually, I'm running also a student branch chapter in my university, and some of my students are now joining from the online, and I have been pushing my student to invite distinguished lecturer, but they they are having a hard time. So that's the one of the reason why I quickly accept your invitation, because I guess you might have had the same problem. But anyway, I congratulate on this opening your new chapter. I believe that IEEE would give you a lot of benefit for the career development. And I heard that the chapter activity in India is performing so well in the global wise. So I really respect your people. That your service into this IEEE, and I think you made a right choice to pick IAS, because I'm a part of the IAS IPCC Industrial Power Converter Committee, and IAS has been renowned for practical academical work both in industry as well as academia. So I really welcome all of you to join IEEE IAS student chapter. Okay, today I'm going to talk about medium voltage drive topology design and control. And the subtitle is Essential Engineering Part in More Electrified Heavy Industry. I don't know if you are familiar with this large size of medium voltage drive, but I hope that this presentation will make you familiar with this medium voltage drive system. I think I'm going to finish my presentation in an hour. So does that sound good to all of you?
Yes.
Yes, sir.
Okay. And then whenever you have a question, you are always more than welcome to ask me your questions. Okay. I'm going to start my presentation with just some questions. So what do you think it has been the largest motor drive in the world so far? I mean, what do you think the size of a motor drive, largest motor drive developed so far? Do you have any idea? I see some of you, smiling. So, is there anyone who can give me a best shot? Is it more than 100 or 50? I'm sorry?
100 megawatts. 100 megawatts.
100 megawatts.
Wow. So Indian people are so smart. It's 101 megawatt. This is a synchronous motor. This is synchronous motor. And you may, ask me what type of application is this? This is a photo of the site, involving this motor drive. This is a fan blowing wind at transonic speed, and you can guess simply that this is built in NASA. This is called NASA wind tunnel. It's just like a fan, but it's blowing the wind at such a fast speed. And this is to simulate the performance of aircraft at transonic speeds. So here you can see the wind tunnel here. In JBNU, which is my university, also has this wind tunnel, but the size is around 100 kilowatt. But that 100 kilowatt design was so hard. So I can imagine how difficult it was. This is for 101 megawatt, the synchronous motor drive system. So I think this was delivered before my working time in ABB to United States. And what type of motor drive system can you think about? Like this is load commutated inverter based on thyristors. I know that young engineers like you are not so much familiar with thyristors, but the medium voltage drive system, thyristors are even now heavily used. And this is a simple single line diagram. You have this this Y and delta of input transformer, and this is a tertiary transformer winding, and you have a parallel connected, 6 poles, a load commuted inverter connected back to back. So this means using this configuration, this provides higher voltage than the single unit, and this is rectifier system. So this is an excitant system to supply the field current, and this is tuned filter because this system has a lot of fifths, 7s and 11s and 13s harmonics. So this is in order to filter out those harmonics. And the motor rating is around 12.5 kilovolt, 2.8 kiloamperes. And as you can see from this schematic, this is 12 series connected thyristors. That means you can see this single thyristor, but this is not a single. You connect 5.2 kilovolt thyristor as many as 12 to support to 12.5 kV. So medium voltage drive system, series connecting the power electronics devices is very common, and this is actual photo of that 12 series connected thyristors. You can see here there are 6 so-called valve, and each valve consists of 12 series connected thyristors. So the reason why I brought up this issue is I like to give you the feeling of how large this system is. So because of this size, there are many special things that are not seen in a low voltage drive system. So that determines the topology as well as the control technique employed in the motor drive systems. Well, this 101 megawatt is, of course, the largest one. I don't know if there has been any larger device developed so far, but this 100 is extreme cases. So what about on average scale? How large is motor drive system? So I checked, the internet, and then got some, the revenue share. So above 7 megawatt, there are 20% of a medium voltage drive supplying 7 megawatt. And then, so 101 megawatt, the example that I've just explained, is belonging to these 20%. And between 3 and 7 megawatt covers around 20%. And then between 1 and 3 megawatt covers 35%. And then rest of 1 megawatt cases covers 25%. So the median lies somewhere around here. So you can think about these days, medium voltage drive, the most common type is around between 1 and 3 megawatt. And there, in the world, some people call this large motor drive system, and some people call a medium voltage drive system. And so some student might wonder why we don't have a high voltage or low voltage instead of medium voltage. Well, large motor drive requires the drive system of a large power, very large. So, as an electrical engineer, large power means either high current or high voltage, right? But high current, is not a usual practice because of cooling and switching at high current. And especially cooling problem is very difficult. In medium voltage drive system, the cost portfolio, usually 50% of the cooling problem comes. So sometimes we just make fun of our work that, we are not electrical engineer, but mechanical engineers, because medium voltage drive system, how you design cooling and bus bars, the layout, cabinet design, these are so important. So dealing with high current is very challenging issues. So naturally, engineers, pay attention to high voltage instead of high current. Well, high voltage has also a problem of insulation, but as compared to cooling, insulation coordination technology is more mature. So, in general, engineers of a medium voltage drive system push high voltage instead of high current. So high voltage, low current brings more compact cooling system, and that leads to why we use medium voltage drive system. Some people may argue, well, anyway, we use high voltage and we use step-down transformer. So, but when I'm talking about the voltage, I'm talking about the voltage just at the front end side of the converter. So downstream of the transformer. Okay. So of course, in the primary side of the input transformer, you have a high voltage, but I'm not talking about that side. I'm talking about downstream of that transformer, which is directly connected to the converter. And this medium voltage drive technology usually classified from 2.4 up to 13.8 kilovolt. And to my best of my knowledge, medium voltage drive system above 13.8 is not available because of the lack of the semiconductor devices, unless we use series connection of the multiple devices. But series connection is not always feasible because you cannot share the voltage equally. So I did the same search, but this time the voltage. What's the typical voltage rating for the medium voltage drive? Like a 3.7 kilovolt covered 34%, and between 7.1 and 14 kilovolt covers another 33%, and then the rest of the voltage, like 14.35 kilovolt, lies around 33%. And why do we need such a high voltage? This 14.1 and 35 kilovolt, usually application is found in oil and gas, like offshore oil drilling site. So it's very harsh environment. So in this case, in median is lying somewhere here, 7.1 and 14 kilovolt. So we can say that the power range is around 1 and 3 megawatt, and the voltage range is 7 and 14 kilo. That's the usual range of the medium voltage drive system. Okay, then what are the application fields for the large motor drive system? So I just gave a rank. So the most popular application field is compressors. So if you look around, these compressors are used very heavily in the power plant side. And then conveyors and mine winders. So it's like mining is like what do you call in English? Like it's lifting up the mine. And you will be surprised that mine. These medium voltage drives are very, very heavily employed. And blowers and fans and wind turbines can be classified as also medium voltage drive system, and pumps and extruders and mixers and crushers and tube mill and ship propulsion. This is also important these days. And soft starter for large machines in the power plant are also a typical application field for the medium voltage drive system. So we can tell that medium voltage application field is quite various in industry field and heavy industry field, very much sophisticated process-oriented field. And I'm going to explain some financial side of this medium voltage drive system. What's the global market size? It's not that big, but it's not also small. It's 1.5, between 1.5 1.6 billion US dollar in last year, and its growth rate can be expected to be around 3.8 and 4.0 So some people say this is not like a fancy area, but I'm seeing that this is important area having steady growth rate. And as Asia Pacific region is fastest growing market, so as we are both belonging to this region, so we should be very good at this technology to support our industry. And what are the key players of this medium voltage drive system, like ABB, Rockwell Automation, Schneider Electric, T-Mike from Japan, Siemens, Honeywell, and Fuji Electrics. And as compared to other industry field, I can tell that this entry level is very high. So it's not easy to for the venture technology to become successful in this field. So these area, there are very classical players, and the competition is very fierce among these players. Okay, so I just gave you a general introduction of a medium voltage drive systems, and then now I'm going to talk about the interesting part for all of you, like what kind of power converter topologies are we are using for this? Is it 2-level, 3-level, or what? So I'm going to explain this. And I don't know if you have heard of the device called IGCT. This is very much preferred semiconductor unit, especially in this field. So I like to give you some explanation of this IGCT. And then the thing I have discovered and then explored together with my teammates in my university flyback type snubber for IGCT. And then I like to wrap up my talk with the conclusion. Okay, so let's talk about topology. So when we means in engineers, when engineers job is trying to design topology. First, one has to determine whether we are using voltage source inverter or current source inverter. Current source inverter, actually this load commuted inverter can be classified as current source. And current source has been enjoying a lot of application field in this medium voltage drive, particularly by Rockwell Automation. So this medium voltage drive system is different from low voltage drive system, such a way the current source inverter is still now playing a key part here. And also this topology depends on power semiconductors. And power semiconductors, power electronics, we are heavily depending on power semiconductors, like a silicon carbide, gallium nitride can change the whole perspective of our engineering field. Same thing for this medium voltage drive. So, the engineers should look for the good power semiconductors. There is the IGBT, IGCT, and IEGT. IEGT is the device developed by the Japanese colleague. And this is more like a marketing side of the topology. And global-wise, these days, supply chain is becoming very important. So every company now trying to use module concept. So what type of module can be friendly with this topology is important. So sometimes called PEP or modular design, something like that. Why is this supply chain friendly? Because once you make module and then use for a variety of power ratings, and then you don't have to buy multiple devices. You just buy single devices and make a nice PEP and then use for these PEP for a variety of components. So it can make supply people very happy. And intellectual property is also important here, which means if some competitors own IP issues, then other competitors cannot use that topology. So the one big example is cascaded H bridge type. This topology was originally developed by Robicon in the United States, and this has been enjoying quite a long time. But now it has been open to public, so now almost all key players have this cascaded edge bridge type, product. So before I talk about topology, I'd like you to consider these four main important factors. So most manufacturers have his own product portfolio based on this favored topology, not because of their performance, but because of like supply chain issues, IP issues, and power semiconductors, things like that. So each company has its own favorite topologies. I'm not, with this limited time, I cannot give you whole perspective, but just I like to use ABB as an example. Why? Because I used to be an ABB engineer, so I'm familiar with the ABB solution. But that doesn't mean, I only talk about a few examples because ABB is the leading manufacturer in this field and mostly cover all the topologies in the market. So I think I can give you a pretty good overview on ABB topology. Okay, this slide is so important. This slide shows, all the topologies manufactured by ABB. And I think this covers almost all topologies available in the world so far. And I'm now going to introduce, one by one, starting from the, high voltage and low power, which is called ACS 580 medium voltage. And what type of semiconductors is this using? This low voltage IGBT. And this topology, I don't know if you're familiar with this topology, is called H-bridge cascade. And why H-bridge? This is H-bridge, and it's cascaded like this. And this topology was originally developed by Rubicon in the United States. And this has been so successful. Why? Because this is based on low voltage IGBT. So the engineers familiar with IGBT can stack up these to meet a variety of product requirements. So design-wise, this is pretty simple. And in all days, and especially now these days too, this has some disadvantage. As you can see here, this is transformer, and this transformer looks very complicated. And this transformer require because of we need a isolated DC source. So we need a transformer to supply isolated source, and this winding has been like phase shifted in order to reduce the harmonics at the upstream. And this transformer is very much customized design. So this has a lot of quality issues, and the supply wise, this is very difficult to employ. So most of companies are having a hard time with this, this transformer. So this is very, ironical that it's not power electronics, but always some transformer that makes people, very hard for this designing issues. But as I told you before, this is so much preferred topology because it's easy to design for the engineers like you. I believe that some of you are sitting in the lecture room have experience working with IGBT before. Now can simply work with this H-bridge cascaded inverter type. Next one is ACS 1000. This is relatively covers lower voltage than H-bridge, but then a higher power, and this is typical example for IGCT case. And this upstream is diode rectifier, and then this is the general 3-level neutral point clamped inverter case. And this is RCD snubber for unique to IGCT, and the common mode filter, and this is shutting down IGCT for the protection issues. And between ACS 1000 and ACS 550, there is a ACS 2000. And so it's a higher voltage than ACS 1000. That's why now 5-level and PC are considered. And this is based on medium voltage IGBT, not low voltage, medium voltage. So because we are using medium voltage, we don't need to cascade it, and we only need to use 5 level. And this topology is also property of ABB. It's some kind of hybrid between NPC and flying cap to supply 5 level. And this ACS 5000 so far covers the largest power as well as the highest voltage. And this is also based on IGCT. Then this is some mixture of H bridge and then 5 level MPC. So this is the H bridge and cascaded. So neutral point and 3 level. And this is isolated DC power supply and 12 poles. And you may have noticed that the topology that I covered a few minutes ago are all unidirectional. So we need a braking resistor to support the bidirectional power flow. But ABB has a ACS 6000. This is also based on IGCT. This has an active front end, so that the bidirectional power flow can be achieved without requiring a dynamic braking resistor. And this ACS 6000 is heavily used in electric ship propulsion systems. And the last but not least, this is a Mega Drive LCI, which I have explained at the beginning of my talk. This is based on Thyristor technology. This was used for the wind tunnel. And as you can see here, you can cover fairly large power and voltage. But this is almost 100% is customized design. So based on customer request, the number of the component and size is carefully designed. So this is like a engineering product rather than just off-the-shelf product. Okay, so this is based on Thyristor. So I pretty much cover. So you have seen like a multi-level, 3-level, 5-level, cascaded, things like this. So multi-level inverter is playing a key role here. And I'm going to explain IGCT. IGCT looks like this. So for the person who sees these, for the first time, see, wow, there are so many capacitors and the components here, and this doesn't look good. Yes, the reliability was quite an issue with this IGCT. And let me explain with the name first. Integrated gate commutated thyristors. So it's confusing with IGBT, right? IGBT stand for integrated gate bipolar transistor, something like that, right? If I am not incorrect. Okay. So actually, I work together with inventor of IGCT in ABB, and I asked him, why did you name IGCT? It's confusing with IGBT, and he told me that that's exactly what they wanted. ABB people thought that this can compete against IGBT. So that's one of the interesting story. But IGCT, simply speaking, it's GTO, gate turn-off thyristors. Same as GTO, but with enhanced turn-off capability. I don't know if you're familiar with the GTO, but GTO is quite notorious for bulky size of the drive current. So the drive is pretty much difficult. And why? Because you have a drive system located in distant part, then it causes a variety of problems. So ABB people solve this problem by a simple idea. Just they put a drive system as closely possible for this GTO. Well, So it's located in the same PCB. And this PCB is handling so much high current. Now you can understand why we need so many devices, MOSFET in parallel. So this gate unit is supposed to drive high drive current, and because of this such a close connection, the leakage inductance is so small. So theoretically speaking, this IGCT is acting like a thyristor during turn-on time, and then during this transient time, the drive current is, the beta in transistor is theoretically 1, which means the base current is same as collector current. So that, it can quickly turn off the thyristors and quickly change it into transistors. So because of this, huge drive capability, it can enjoy low conduction loss of thyristors and then, low switching loss during transistors. Of course, this cannot outperform IGBT for the switching loss, because IGBT, we are talking about switching frequency of 10 kilohertz, 100 kilohertz. But this this IGCT switching frequency is usually below 1 kilohertz, somewhere between 300 hertz and 700 hertz, something like that. So switching loss is not that important in this area, but the conduction loss is so important in this case. So where is this IGCT position? IGCT has been developed for last, to be exact, late 90s. So it has been more than 30 years, and it has been so successful. So ABB has been enjoying a lot of revenue because of this IGCT. So personally, I think this is a very nice device. So this is not as fancy as IGBT, but it's improved devices of GTO, and you will see that still there are a lot of application field for the medium voltage drive. I don't know if you go some part of the world, they don't even use drives; they just use line starting concept. So the same thing, like in some part of the world, some people still use diode and use mechanical variables like a saturable reactor, things like that. So in this case, IGCT can play a huge role. So I believe there are lots of application fields that we can use this IGCT. Gallium nitride and silicon carbide, we think that those are very fancy, but the actual application field is very, very limited, and we should pay attention to these GTO and thyristor and IGCT application field too. And what are the advantages of IGCT? Well, because of these GTO thyristors, the high current turn-up capability, and is almost 3 times as high as IGBT. It means, if you need 3 IGBTs parallel connected, you can just simply use 1 IGCT, so that you can simplify mechanical bus bar and cooling system. You remember that I commented that it's not only electrical system but also like a cooling and mechanical system that give a lot of cost. So it's important to streamline and simplify the mechanical bus bar connections. This is a example, like in IGBT, we have a 6.5 kV IGBT. And this maximum RMS is around 20, 30, and this is 4,340. So it's not exactly 3 times, but 2.3. But engineering-wise, we need 3 IGBTs, and because of we cannot guarantee even sharing of the current. And this is also IGCT comes as a press-spec technology. Press-spec, press-spec. IGBT these days also use soldering. So from the outside, and then you solder. And solder means, it's very is weakest link for the whole module technology. So below like thermal cycling issues, then IGBT might go failure mode. But this Perspex technology does not have any, the soldering, wire soldering issues. So it can sustain larger short circuit capability and better cooling capabilities, and reliable protection and simpler cooling system. My lab has been doing a lot of experiment using IGCT. My student has never seen IGCT blowing. But power electronics engineers are having a hard time with the IGBT blowing a lot of times. But in that case, I think a Perspex technology is much more preferred solution than an IGBT. So IGCT offers simpler and then cheaper mechanical and cooling systems. And recently, 10 kV IGCT has been developed, and actually this was not recent. In 2005, the prototype was developed and was confirmed and was released on IAS magazine. And one of the authors, Dr. Peter Steimer, and who worked together with me during my ABB employment time. And but then that time, this device was put into refrigerator. Because ABB people wanted to develop topology rather than these devices. So they developed 5-level, things like that. But now I brought up another attention to this, and then I worked together with ABB people, and I revived this 10 kV IGCT because I think it's the right time. Why? 3-level MPC employing 6.5 kV IGBT or IGCT have been the most common choice up to 7 MW. So it's okay. But now we have discovered a lot of application fields such as wind turbine and also grid, grid following and grid forming inverter requiring more than 7 MW. Then I think a 5-level is too much, and then also why don't we need this 10 kV IGCT so that we can easily cover drive system more than 7 MW. So that was the biggest motivation for me and ABB people again to develop 10 kV IGCT. So this has been developed once again, but we found a new problem, which is this is single source and specialized gate control interface and specialized mechanical and cooling design. Well, these problems were there before 10 kV IGCT, but this turn-on DIGT limitation become more problem. It's severe with 10 kV. Now, what is turn-on DIGT limitation? Because of this Iris technology, when you turn on the device, you need to limit the turn-on rising time of 10, below 1,000 up to 1,900 amp. If I explain in more, practical way, if the turn-on slope is so fast, then thyristor suddenly turns off because of the hot spot. So how do we limit this limitation? We put an inductor, right? And this, if you put inductor in series with the switch, then you are having a problem when you turn off because it will cause overvoltage spike. So we need a overvoltage snubber, and this undermines system efficiency and cost. So ABB and JBNU engineering team have noticed that, okay, 10 kV IGCT is great, but we are suffering a lot from this turn-on DIGT limitation because as the more higher the voltage, the higher the turn-on limitations. So JBNU engineering team has proposed some new concept of flyback type snubber to improve system efficiency and cost, so that the medium voltage drive system efficiency can be also improved. So the last part of my presentation is dedicated for this flyback type snubber for IGCT. So let me summarize why do we need the IDT. Actually, if you look at medium voltage drive system, you will see some snubber structures which were not seen in low voltage drive system, and that's because of this reason. As I've explained before, when you turn on the current, and if the turn on the IDT is more than the spec, then it might lead to localized hotspot and unwanted turn off. This is very dangerous. So you need to maintain this turn on slope below that level. And as a power electronics engineer, we all know that when you turn on the switch, sometimes it means turn off for the diode reverse recovery action in somewhere else. And this diode is a more limiting factor than switch. So we need to limit that turn on slope of the switch, which is turn off slope of the diode. Otherwise, diode would have a huge reverse recovery problem, resulting in melting or burnout. So this is the usual way of limiting the IDT. Here, the IDT snubber is here, right? And then when you turn off, we need to bypass the energy stored in here. So this is called RCD snubber, and everybody knows well about this, and this RCD snubber. And this RCD snubber, this power rating is for the one IGCT is a few kilowatt. So we are talking about a few kilowatt power loss, and this resistor is water cooled. It's called submarine resistor. So price wise is a very bad, and also the volume wise, this covers some space of the medium voltage drive cabinet. Okay, so what's flyback type snubber? So this is a conventional structure, and then I simply replace this RCD snubber with this flyback type snubber. I know that you are familiar with flyback. Flyback, in DC-DC converter is providing the energy stored in magnetizing inductance to the secondary side. But this time, it stores the energy and then feeding back to the DC link, so that it theoretically it does not have to dissipate the power. And where is the inductor? And here there is an internal magnetizing inductance, which is limiting this turn on the IDT. So if I explain in more detail, when you turn on, this magnetizing inductance will limit the DIDT, and then when you turn off, then this magnetizing inductance will discharge current through the secondary side, which is connected to DC link. So it can function both as limiting the DIDT as well as feeding back the energy to the source. So we, together with my student, I designed the flyback type snubber based on the 3 design requirements. So I like to maintain the over voltage spike across IGCT below the spec, and also discharging time of magnetizing inductor is less than the switching frequency and the voltage rating of clamp recovery diode, something like that. And then always, there are some new problems, which is like if we put flyback transformer, there are always leakage inductance available. No matter how you close, you put this transformer, and this leakage inductance will eventually require another RCD snubbers. Well, but since this is leakage inductance is not that large as compared to magnetizing inductance, the new RCD snubber does not have to be large as before. So this since the size is a lot reduced, this can be mounted just close to the stack design. So this is very simple mechanical design. And the other challenge was now this diode. This diode is experiencing very high voltage during turn-on time. So how high is more than like 10 or something like 15 kilovolts. So we have nothing but to use some multiple winding to share this voltage stress to each of these diodes. So this multi-winding solution was the one we have worked on so far, and then we did the experiment, and then we published some papers based on these multi-winding solutions. And this photo shows some experimental setup in our lab. And this is IGCT stack for the 3-level NPC. And this is a flyback type transformer, and this is a DC link cap. And then we are doing the test for the single pulse test. This is the inductive load. And for the single pulse test, we usually perform double pulse because we like to do turn on while the current is not recovered to zero. And this is a simple experimental setup doing the double pulse test. Of course, in the university laboratory, we cannot do steady state continuous pulsing because of the lack of the input power and the load. So double pulse test can give you a fairly large the verification result for this experimental setup. And we first perform RCD snubber, the classical type first, the classical type, and it works fine. So we verify that our engineering setup is doing okay. And then using the same engineering setup, now we perform flyback type snubbers. This was single winding and multiple devices, and this is multi-winding and single devices. Of course, we like to know that whether these can share the voltage. And here, this is a rectifier diode, stress, but now this is equally divided into two devices. And when we use two devices cascaded, it's not sharing the voltage equally, but these multiple winding cases, this device have equal sharing of the voltage. I'm sorry, I'm going a little bit fast because it looks like you're losing attention, so please forgive me. Okay, so energy saving by flyback type snubber. That's the major goal. So we compared for the case of 7 megawatt 3-level MPC, and this is loss breakdown. Diode consumes 24.6 kilowatt, and IGCT 30.5.4 kilowatt. And copper, what is copper? This is inductor, the copper loss of that flyback type snubber, and this is RCD. 13.5 kilowatt power loss. And if we use flyback type snubber, this whole RCD is gone. But instead, we are using core. Here, this inductor was air core, but now we are using this core loss because we need a tight coupling between primary and secondary. And we introduced this 2.6 kilowatt, but our saving is better than our losing. So at the end, flyback type snubber can save energy by 10.9 kilowatt, which amounts to be 0.16%, and that's huge in these very efficiency-oriented applications. Okay, let me wrap up my talk. So. Medium voltage drive technology plays an important role in many industry fields. I think you have no doubt on this. And then world market size of medium volt drive is growing fast. And in my personal opinion, it's not because of market size, but these days we are having a lot of trouble with the supply chain. You know what I mean? It's not easy to buy component from one country suddenly. So every country should be flexible to maintain its own technology, so that it can, supply the important product to its own market. And various multi-level topologies and power semiconductors are employed in present medium volt drive system. I have covered some of the important topologies and power semiconductors. And 10 kV IGCT is expected to play a significant role in a niche market of 6.9 kV, 7 mega and above. So I like you to pay attention to this IGCT. I think this is very underestimated device in this field. And also I believe that India, there are a huge market for the mining and also a heavy industry. So it makes sense that the young engineers like you to prepare for your career development in this medium voltage drive system. And also don't forget the snubber is an important issue in this medium voltage drive system. And not only this flyback type snubber, but also other types of snubber are very important. So it makes sense to pay attention to this snubber structure too. And this covers some of my references. And I don't know if I gave you a right impression of this medium voltage drive system, but hopefully you enjoyed my talk. Thank you.